One. Am I audible?
Yeah, it's you are audible. Dr. Nikhil Aggarwal ji.
Yes, sir. I'm definitely audible.
Yeah, thank you, thank you. You both have accepted our kind invitation.
Most
And
welcome, sir.
Mr. Prashant, Miss Ayushi Prajapat,
She's here, sir. Actually, right now she's doing an experiment, so she will join us at the right time when she has to
okay.
demonstrate
The main
software.
motto and what we will be expecting from Dr. Nikhil Aggarwal ji as well as Professor Prashant Singh ji, few of our students, it will help us. They will get trained on DFT. With these few words, I once again welcome you and all the participants and my fellow colleagues. Without wasting much time, we will proceed further. Thank you.
So thank you. First of all, I thank you, Professor Arjison Kodesar, for encouraging us to organize such a workshop for all the research scholars and students. So with this short inaugural program, I request Dr. Aggarwal sir to start his session. Thank you.
Hi, good morning to all of you. Dr. Nikhil this side. Thanks for the warm welcome. Before I enter into the technical part, quick confirmation. My slides are visible to all of you.
Yes, sir, they are
Yeah.
visible.
Chaliye. So, thanks to all for the warm welcome. We are over here in a national workshop on DFT modeling for the material scientist, which is being scheduled by the Shivaji University for 1 day. So, before taking much time, I'll directly move on to the topic of my talk, which is the materials modeling using the DFT approaches. The fundamental calculation using the quantum espresso software package. So before we enter into the technical part and the details of what exactly is the DFT, the Corn-Share model, what kind of materials we are going to detail, what kind of properties we are going to compute, brief introduction about what we basically do at CACR New Delhi. So at CACR New Delhi, we are involved in the in-depth electronic structure calculations of controlled molecular aggregates toward their application in OLED-based materials, photovoltaics, catalysis, energy-based materials, and the optoelectronic devices. So these are just few of the applications we consider while doing the DFT calculations. Here are some of the representative research articles we had published on DFT modeling. So now we'll start with the fundamental of what exactly is the DFT. So I'll take only 10 minutes for a theoretical discussion, and then we will move on to the practical part. So meanwhile, as like I requested to the Professor Mansingh that if some of the participants can work parallelly with us on the laptop machine, that will be great. Otherwise, I think we will be providing the lecture recording to the participants so that they can work after the session also. So, coming to the main parts, so the objective of the talk is to deal with the materials modeling. So, when we say materials modeling, basically we are going to learn in the next 2.5 hours that we will be making the property of solid state materials. Solid state materials, as in they will have their periodic structures in the form of SIF. Then I'll take all of you toward the nanosystems. Nanosystems, specifically the nanospheres, the two-dimensional sheets, monolayers, and the multiple layers, then some heterostructures, and then correct. So these are the kind of materials we are going to study in the next 2.5 hours. So what kind of properties we are going to study? I'll first start with the SCF convergence calculations, which are the most fundamental calculation before we start up with the main calculations. Then I'll take all of you toward the electronic structure calculations, mainly on the band gap analysis, band gap computations using the DFT model. Then I'll take all of you toward the structural optimization, which will be basically helpful for the novel, newly designed materials. And then we will move on to the magnetic studies. Then I'll take all of you toward the designing aspect, the designing aspects of three different type of materials I highlighted. the nanospheres, the layered materials, and some heterostructures. And then finally, we'll move on to the band structure calculations. We'll see some results onto that. And then finally, I'll move on to the molecular dynamics calculation using the DFT model, which are pretty rare. So what kind of results we are going to obtain from the molecular dynamics, we will detail. So huge list of properties are there, but I'll try to be within the time frame. So basically, we can compute the properties of these kind of materials, materials which we have enlisted using two different type of model, the quantum chemical model and the molecular mechanical model. Definitely, I'm sure all of you must be aware of it. So quantum mechanical model, they basically relies on the well-known Schrödinger's equation. However, the molecular mechanical model, they relies on the Newton mechanics law. As in, under the molecular mechanical model, we treat the atom just like a balls of some rigid mass m, and we treat the bonds with some spin constant values of k. So, as in the molecular mechanical model, we treat the molecule just like some kind of ball and spring. On the other hand, in the quantum mechanical model, we detail the atom with their all interelectronic repulsion terms, kinetic energy, potential energy terms. So definitely the quantum mechanical model, they has the upper hand in terms of their accuracy. But at the same time, the more the accuracy we need, the more amount of time we need to provide for the calculation. So uh, whenever we want to execute any new calculation, any new project, there are certain questions which we have to keep in our brain. Basically, what we would like to compute, how much accuracy we need. It doesn't mean that we'll go for that high accuracy result and that will take a lot of time. Similarly, if we want to minimize the calculation time, what kind of approximations? So when we say approximation, it dilutes the accuracy, but we need to see how much dilution is acceptable in the literature. So what kind of approximations we are going to use? So these are the initial things we have to keep in the brain. Now, I'll skip this slide because I'll be main focusing on to the practical part, the Schrödinger's equation, the molecular mechanical models. So I'll just brief about this slide. So in this slide, this is the published result, I think somewhere around 1995. In this particular slide, the researchers have highlighted different type of quantum mechanical model, or you can say quantum chemical model. It has Hartree-Fock model, as in the HF model. Then you have got the Muller-Closet model, couple cluster models. So why these are the different models? Essentially, we have the objective to solve the Schrödinger's equation. Now, the Schrödinger's equation can be solved without using any approximation, or it can be solved with a some approximation. As in, I'll simply put up one example. If we have to evaluate the value of 1 by, let us say, 1000, we can immediately reply with a value of 0.001. But when it comes to the finding of the value of 1 divided by 998, that becomes a great time consuming calculation. So, but other way, what we can do it, we can always approximate it. The value of 1 by 998 equal to 1 by 1000. So using this approximation, the values will be similar to each other, as in 0.001, 0.001 point something. Using the approximation, the calculation time definitely decreases, but there is a compromise with the accuracy also. So in this particular slide, what is being highlighted, that as we move from the HF model to the Muller-Closet model, the DFT is missing over here because they have not studied the DFT model. DFT comes in between the MP2 and the CCSG. I'll detail what exactly these parameters are. So moving from HF model to MP2 model to DFT to CCSG model, as we see the values of M square, M5, M6, M7, it increases. Basically, they are the scaling of cost. If you plug in the value of M is equal to simply 2, you can see the magnitude increases from HF to CCSG. Now, what does it mean? It means that moving from HF to MP2 to DFT to CCSG, the calculation time tremendously increases. And this is not like a linear increase. And as the calculation time increases, it hints that CCSG model are highly accurate model because they are very less approximation embedded. On the other hand, HF model, they are highly approximated quantum mechanical model, take very less amount of time. DFT comes in between the HF and the CCSG model. That means there is a little compromise with the accuracy, but at the same time, the calculation time, it is in between the CCSG and the HF. So you can do the meaningful calculation with the acceptable accuracies. Now, coming to this slide, over here, this is again the published result. Over here, the researchers have shown that uh, taking up to 100 number of atoms in a system. Now, not only the number of atom, although it depends on the number of electrons also in the system, but they have investigated in terms of number of atoms. Moving from, let us say, 1 to 100 number of atom, the CCSG models, they are the appropriate, you can say, model. However, moving from 100 atoms to, let us say, up to 1000 number of atom, the approximations we need to provide more toward the Schrodinger's equation solution, and accordingly the DFT models we will have to use. Similarly, moving from, let us say, 1000 number to 2000 number to 10,000 number of atom, even the quantum mechanical calculation become more and more trivial, so we need to provide more and more approximation, and then the molecular mechanical model, they become more and more useful. So in a summary, that if you are working on the system wherein the number of atom lies in between, let us say, 1 to 200, 300, 400, the DFT calculations are the optimal one. Taking less number of atom than, let us say, 20, 30, the couple cluster models you can apply. Taking more than 300, 400 number of atom, DFT has a trouble in terms of calculation time. Otherwise, if you have the access to the supercomputer, you can definitely employ the DFT for the larger system. So that's all a little bit of the theory. Now I'll come back. Now I'll come to this side. So our focus in the present talk is to study the properties of some kind of material which we enlisted at the beginning of the session using the software package. So in literature, you will find that there are couple of software which predict the property of these kind of material, the properties which we enlisted. You have the VAS, you have got the Schrodinger's, you have got the Win2K, you have got the Material Studio, and there are not many software which are available in the literature. What we basically use, we are using the software named as the Quantum Espresso. Now, why specifically Quantum Espresso? Because it's an open access software. All of you can definitely use it free for your academic purpose. It models the property at a quantum mechanical model, quantum mechanical theory level at the nanoscale also. So that is the upper end in terms of Quantum Espresso. You don't have to pay any huge fees toward the licensing of the given software. Now, what kind of properties the Quantum Espresso can compute? It can compute the ground state calculation. It can do the ground state calculation as in the structural optimization, the molecular dynamics, the potential energy surfaces, which are useful to estimate the intermolecular interactions, the electrochemical part. Then you can do the TDDFT calculation, the vibrational calculation, phonon calculation, and there is a huge list of properties which you can estimate using the Quantum Espresso. But definitely now at this point, the question comes that if the Quantum Espresso is an open access software, will there be any compromise with the accuracy of the result as compared to the paid software? So what you can do, you can just have a look onto this research article which was published long back in 2009. This research article enlists about the capabilities of the Quantum Espresso by the developer, and till date, the citation, if you look at it, has overpassed around 34,000. So I don't think so there will be a question on the accuracy of the result which the open access software it provides. So Quantum Espresso robust software for the electronic structure calculation at the nanoscale, open access, highly cited, highly accurate models. So at CACR, we are providing the training to the participants on these DFT modeling, different kind of modeling, starting from the Quantum Espresso, the molecular modeling using the Gaussian software, and lot more courses we are providing over here. And ended the Quantum Espresso based training is the most sought training in our research center. Overall, we have trained till now the 7,600 participants, and out of 7,600 participants, I can see that close to half of it have opted for the Quantum Espresso based training. So a graph which says that over the interest in learning the Quantum Espresso based calculation, it has increased month wise. Previously, we used to get around 50-60 participants, and now every month if we look at, we are crossing around 500-600 number of participants. So highly robust software, easy to learn, easy to apply in your research. So we had some couple of talks at our research center by the experts from the IITs. We also delivered some lectures at different institutions on these DFT modeling. We have also obtained the ISO certification, trained these many participants. I'll just keep it out. The participants from these universities have attended the training. Experts who have also attended the training at our institution. These are the few faculty members and the research scholars who have joined our training in the last few years. Professor Dilip was there. I remember he was there in our XRD batch. Professor Mansingh was also there. Professor Mukesh, Satyajit, Kabir, they had all joined our DFT batches. And then there were scholars under, I think, postgrads were also there. Great. So now I come to the main point of the present talk. The properties and the systems we are going to investigate in next couple of hours. So basically we divide the training into two parts, as in the part A and the part number B. In part A, we focus on to the designing of the systems along with some software installation using the Avogadro software and the Vesta software package. So basically, in the 10 days of the training program, the 10 hours of the training program, we start with the designing of these systems, starting from the nanocrystal of ionic systems, cationic and ionic rich nanosystems, the neutral one, the gold nanoparticle of variable sizes, the designing of the monolayers and how to model their properties, because monolayer modeling and the DFT model, they become a little difficult task, because using the DFT with a monolayer 1000 number, 2000 number of atoms, so therein we are going to introduce a new concept, a concept of unit cells of the monolayer. So how to use that, we will have a detailed discussion onto it. Then how to model the multi-layers, as in the bilayer, the tri-layers, then the nanowire one-dimensional particles, some heterostructures. So these things we discuss on day-wise manner. And then we discusses about what exactly is the pseudo potential we use in the quantum espresso, the plane wave function calculations, kinetic energy, charge density cutoff value estimations, atomic substitutions, the band gap estimation, SCF convergence, the band gap for the neutral system, the N-type, P-type semiconductors, ionic crystals, organic molecules, nanoparticles. So these we discuss usually on day number 6. Then all the kind of structural optimization, VC relax, non-VC relax, the band structure calculations, then the magnetic moment calculation, nanocluster DFT pools, effective mass calculations of electron and the hole, their corresponding mobilities, the density of states, transition probabilities, intermolecular interactions, and all these kind of studies. But we have a little time as compared to what we conventionally take, around 2.5 hours we have. So instead of taking all the properties which we have invested over here, we will be focusing on to the properties and the system listed over here. We will start with the designing of the gold nanospheres. We will discuss the concept of nanocluster unit over there, the graphene monolayer structure, designing the units of the monolayer, some heterostructures, and I'll be main focusing on to the property part. The properties as in the plane wave parameterization, kinetic energy, charge density cutoff, atomic substitution, the doping, and the properties which are invested over here. So in total, we need to discuss the 6 properties along with the 3 systems. The 6 properties, as in I'll start with the SCF convergence calculations, then I'll move on to the band gap calculations, then the structural optimization. Afterward, I'll move on to the magnetic property calculations. Then I'll move on to the band structure calculation, and finally on to the molecular dynamics calculation. Meanwhile, we will have a discussion on to the designing part also, the designing in terms of nanospheres, in terms of layer structures, and in terms of heterostructures. So these are the things we are going to discuss practically. So I think I am done with the theory part, and now I'll move on to the practical part. So to operate the quantum espresso, see, quantum espresso has a one limitation also. It doesn't mean that everybody uses it. Quantum espresso has got one limitation as well. The quantum espresso does not have its own dedicated GUI. GUI as in the graphical user interface. As in, if let us say you have to explore something in this Google Chrome window, you can simply type the word and you get the whole sort of information about it. This is not the case with a quantum espresso. Quantum espresso lacks its own GUI, which means if you have to run the quantum espresso based code, you need to learn the programming. But as a beginner, majority of the researchers, research scholars, they rather refrain to learn the programming. So what you can do it, you can always use an additional software which is named as a Burai. Now Burai is again a free open access software wherein you can do all kind of initial calculations or the fundamental calculations for your research article. As the Burai, it supports the structural optimization, band gap calculations, the magnetic moment calculations, the molecular dynamics calculations, and density of state calculation. But if you want to go toward the advanced part as in the TDDFT calculation for the chemical, for the spectroscopic studies, the NED calculations for the transition state structures, for non-calculations, you need to learn the programming, but that comes at a secondary stage. In the present session, we will be learning about how to use the Burai, which is again an open access software use and how to use the quantum espresso within this package. So generally we discusses the installation of the Burai and the quantum espresso also, but limited time. I'll not go toward the installation part. I'll directly jump onto how to use the quantum espresso and a Burai to obtain the properties. So I would like to ask only one question, that is there anyone who is working in parallel with us? Otherwise, I'll take a little speed to complete the objective. Anyone over in the meeting? Online participant, offline participant?
No, sir, you can proceed. Later on, audience will try.
Great. So I'll first start with the SCF convergence calculation. Now, what exactly we mean by this is the interface of the Burai. So you have got a couple of tabs over here. Recently used, it enlists what kind of calculation you have executed. Then the My Computer, it enlists whatsoever you have under the C folder. Then the My Project, you have got the example folder. So we are going to explore this example folder in a minute. In the example folder, you have got three subfolder named as the SIF, PWSF, and the XYZ. I'll be dealing with the SIF in the current session. SIF as in the crystallographic information file. So there are a couple of examples given in this folder. So I'll take the silicon example to demonstrate how to do the SCF convergence calculation. But before that, what exactly we mean by the SCF convergence calculation? So I am sure practically whenever you will be working in the lab, you must be dealing with the stable samples, and the stable samples got very less energy, or you can say huge negative energy. So the very first calculation which we basically perform with a new material or with a reported one, it is a SCF convergence cycle. SCF convergence calculations, it bring down the energy of the system by tuning three variables in this window. So what are those three variables? We will have a detailed discussion about that. Right now, have a look at the few of the options available over here. So note down, the quantum chemical calculations or the quantum mechanical calculations can be divided into 4 steps. Any quantum chemical calculation. The step number 1 is to design the molecular structure. Step number 1 is to design the molecular structure. The step number 2 is to design the input file wherein series of codes corresponding to the calculation will be there. We will detail about each and every step. The third step is the calculation itself, and the fourth step is the result analysis. Step number 1, structure designing. Step number 2, input file creation. Step number 3, main calculation itself. And the step number 4 is the result analysis. Note down, out of these 4 steps, the 3 steps will be executed by the Burai. The step number 1, step number 2, and the step number 4. The step number 1, as in the structural designing, you can do it in the Burai. We are going to do it in the session. The step number 2, the writing, the designing of the input file wherein the series of codes will be there. Then the calculation will be handled up by the quantum espresso in the background. The result analysis again back to the Burai. So let's start with the very first calculation named as the SCF convergence calculation. Great. So this is a lattice we are seeing for the silicon unit cell, which is there in the example library. You can always get more example from the online database. I'll show you in a couple of minutes. So on a silicon unit cell, we are bringing the calculation of SCF convergence. Over here, there are few options we need to see. There is a cell option which enlists what kind of Bravais lattice on which you are working. So depending on the Bravais lattice, the SIF file indicate, you have the option over here. Similarly, if you will be working on some different lattice like the KNO3, as in this is the hexagonal lattice, the software depict hexagonal lattice. Next, it enlists the edge length across X, Y, and Z. I'll directly move on to the element column. Now, under the element column, there is something listed as the pseudo potential. Although we used to discuss a detailed part about the pseudo potential, but I'll just give you the brief overview of what exactly is the pseudo potential. See, a pseudo potential is a mathematical function. I repeat, a pseudo potential is a mathematical function which correlates the electronic structure of the material, with the type of electron an atom has. As in, we can classify the electron into two types: the core shell electrons and the valence shell electron. Core shell electrons, valence shell electron, majority of the electronic based property of the atom, it depends on the valence shell electron. So therefore, accordingly, we have got two type of pseudo potential. The first, ultra soft; second, PAW. PAW named as a projected augmented wave function. Projected augmented wave function based pseudo potential, it correlates the electronic structure with both core shell as well as the valence shell. However, ultra soft based pseudo potential, it only correlates the electronic structure with the valence shell. Therefore, out of PAW and the ultra soft, we primarily select the ultra soft pseudo potential because it minimizes the calculation time. If the result accuracies are not sufficient enough, only then we switch it on to the PAW. So how to select the appropriate pseudo potential? Click over here. There are a couple of pseudo potential files enlisted here. You select the ultrasoft model. Now under the atom, this we need to discuss in a little bit detail. So this is what we are seeing, the silicon unit cell. If let us say you would like to modify the silicon unit cell with the with the group 15 element to make it a n-type semiconductor, pretty easy way. You have all the atoms listed over here depending on their absolute positions. I repeat, depending on their absolute position in the lattice. As in this silicon position, but before that, 1 minute. So over here, we are seeing the silicon unit cell structure. When I click onto this fifth silicon, it depicts that we are having these two opposite face centered atoms. Similarly, clicking onto the first silicon, it shows that this is the position corresponding to all the corner silicon atom. So like that, this is the tetrahedral one. So whichever atom you would like to modify, substitute, you just have to double click onto it. It becomes editable, backspace from the keyboard, and type the element of your choice. That way you can easily bring the substitution in the given unit cell. Similarly, if you want to introduce a new atom into this lattice, pretty easy way. Right click in the screen, click put an atom, and select the atom of your choice from the periodic table. Like let us say if you want to have some group D element, so that way you can also introduce an extra atom in the given lattice. For the simplicity, I'll not take the cases of the doping because that will increase the calibration time. I'll take the silicon unit cell structure to define the properties. So this is the silicon unit cell structure. I hope the doping part, substitution part must be clear to all. Simply click over here, add the atom of your choice. After the geometry, but before that, one more thing I would like to show. You have the option of input file here. Now, what is the meaning of the input file? So, participant, at the beginning of the session, I detailed that Quantum Espresso works on series of codes. So, what you have to do it, you need to learn the programming to write down those code. Otherwise, if you want to bypass that coding, the Burai will do for you. As in, you can have a look onto the input file. At this stage, the input file look like this one. Herein, it first defines the direction or the directory of the pseudo potential. So we have it in some folder. Then it write down the edge length of the unit cell across the x direction. This I Bravis value equal to 1 define that you are working on the cubical lattice. As in, if you move on to the KNO3 lattice, which has got the hexagonal shape, it indicate I Bravis lattice equal to 4. So no doubt, whatsoever changes you are making graphically over here, the input file will automatically get edited. You don't have to play with these codes. Similarly, you have got n atom defining the number of atom depending on their relative positions, absolute positions. N type corresponds to the number of different element in the system. So as in we are working on only silicon, only n type equal to 1. KNO3 has got three different elements. That is why N type value is equal to 3. Then it enlists the value, that it enlists the type of elements on which you are working, their atomic weight, the solar potential file we are taking, and their relative position. So that's how the input file look like. Now, our objective, the first objective is to do the SCF convergence calculation. What is the SCF convergence calculation and what kind of results it is going to yield? We will have a detailed discussion onto that. Before that, have a look onto your input file now. So now the input file has been modified and now it lists what kind of calculation we are going to do it. Now I'll discuss about the SCF convergence over here. Before that, so participant, the very first calculation is the SCF convergence calculation. Using the SCF convergence calculation, we are going to minimize the energy of this unit cell. Now note down, there is a difference between the SCF convergence and the structural optimization. We are not doing any structural optimization at this stage. Why? Because this unit cell structure is being experimentally derived using the X-ray crystallography. So which means the structure is already optimized. How to do the structural optimization, we are going to learn after a few more minutes. So this stage, the structure is already optimized. On this optimized structure, we are going to further bring down the energy of the system. Now, why is it so? Have a look onto some of the research articles onto the screen. So what these graphs indicate, that the energy of the system, the absolute energy of the system, it is dependent on three input variables. What are those three input variables? They corresponds to the value of the kinetic energy wave function. That is the number of the kinetic energy wave passes through a unit area in a given lattice. Then you have got the charge density. Then you have got the value of the K points. So physics people, I am definitely sure that you must be aware of the reciprocal lattice, Brillouin zone, the K points. If not, please see the literature part. So what essentially we are going to do it, we are going to tune the values of these three variables so as to minimize the energy. Why? Because experimentally, if we are working on the stable sample, theoretically also we need to minimize the energy to make it more and more stable. The calculations are pretty simple. What do you have to do it? You need to change the values over here. But before that, there are a couple of options available over here. Restart mode, although the software company claims that you can always pause the calculation in between in the Burai, but from our experience, we could never able to achieve. So therefore, I strongly recommend that not to use the restart mode to do the calculation. Next, you have got the maximum time. The Burai enlists that this much time a calculation may take. Definitely, it will not take that much amount of a time, 10 raised to the power 4. Within a couple of seconds, it will be done. And note down the calculation time depend on the type of a lattice you take, the number of atoms you take in the lattice, the electrons, the periodicity, a periodicity, and so many factors are there. So then you have got these variable. So essentially, in terms of SCF convergence calculation, what do you have to do it? You need to change the values starting from the lowest value which you can take, and then taking a some fixed ratio. This ratio needs to be from 1:4 to 1:12. It depends on the type of elements which you take and the type of unit cell which you take. The smallest ratio which you can take, it is 1:4. The biggest, the largest one, it is 1:12. So I am taking a ratio of 1:10, 1:4. Total charge, I am not defining anything over here because there are no substitution within the given lattice. So I would like to discuss one more thing at this stage. If in case you would be doing any modification in the lattice, let us say you want to modify the silicon with the phosphorus. Modification of a silicon, replacement of the silicon with the phosphorus, bring one extra valence electron in the system. Silicon has got 4 valence electron, phosphorus 5. So one extra electron in the system. Accordingly, you will have to define the charge in this total charge option as -1. Otherwise, if you are not bringing any modification, leave the charge as undefined 0. Now, key points, I am keeping it 2 to 2 only. At this stage, I am not going to change much. Then electrons, we are going to deal with the electrons, which basically follow the Fermi-Dirac statistics. So I'll change the smearing type to the Fermi-Dirac. Next, although we have to tune the parameters over here, but at this stage, I'm not going to move toward that. To run the SCF conversion energy calculation, SCF calculation basically the energy calculation, you need to move toward here and click onto the run icon. And if you want to do the parallel computing, you need to tune the variables, mathematical values here. Otherwise, for serial computing on your normal laptop itself, keep this value only 1 and 1. Next, click onto the save project. Next. So I always recommend that to keep a new folder for each and every calculation, because each and every calculation need a couple of files, and then at the later stage it becomes difficult to isolate and identify them. So better you create files for each and every calculation and just click onto the OK. So pretty easy to use interface. Go to the geometry, I go to the my project, look for the examples. Under the example tuning, whatsoever you want to do it, do it. Move to the SCF option, change the values according to your choices, 3 lines, and then finally onto the run icon. The calculations, they are very fast. As you can see, it is already done. So you have the option over here, calculating. Under the calculating panel, if you are seeing any icon over here, any file over here, the calculation is running. Right now, there is no file icon over here like these icons. So which means the calculation is already over. Let's go with the result analysis. For the results, 3 lines, again the same interface, result. And under the result, you can see that you have got the log file. In the log file, as in the output file, you can see the calculations we have done using the quantum espresso. So some participants, they have always a doubt that, sir, you are always using the Burai, never ever opened the window of the quantum espresso. So are we doing the calculation using Burai or quantum espresso? Note down, Burai never ever does any calculation. Its role is to only design the input file, design the structure and the result analysis. Calculation will be handled by the quantum espresso. So in your manuscript research article, you don't have to highlight that you had used the Burai software. You need to highlight that you had used the quantum espresso software. So the calculation is done. I'll show you the graph. So this is the graph showing the energy of the system decreasing with each and every iteration. The final energy of the silicon system is this much in the Rydberg unit. So give me a minute. Let me see if I have got the result file of it. This is the older one. So this is the file we have. Now, please have a look at the result we are depicting over here. So basically what we have done, we had changed the value of the kinetic energy wave function and the charge density and kept the K point same and monitor the energy of the system. Now, why is it so? Because you may be able to observe that taking the higher value of the kinetic energy wave function and the charge density, it minimizes the energy, making it more and more negative. You can have a look at the graph also. These graph you will have to put up in your manuscript. So this is a similar graph you had seen on these research article, that taking the higher value of the kinetic energy wave function and the charge density bring down the energy of the system. So basically what do you have to do it? From the SCF convergence cycles, you have to obtain the cutoff values of these two variables, as in these three variables. Now what is the meaning of the cutoff value? A cutoff value is the value beyond which energy does not change significantly. As in, if we look at this graph, we can see that changing the kinetic energy wave function all the way from 10 to 35 Rydberg unit, initially the energy decreased huge, and beyond certain point, now it is reaching a saturation. So this is going to be the cutoff value for a silicon cubical lattice. So the calculation is pretty simple. You just have to change the variables over here each and every time. I'll not be able to do those many calculation because that will take a lot of time. So SCF convergence calculation, you just have to change the values here, get the values of these energy, put it over here, and then plot a graph. The graph will tell you at what stage you are getting the cutoff value. This cutoff values you have to take for all the properties calculation, starting from the band gap analysis, magnetization, and the band structure, density of states, so on and whatsoever. So cutoff value estimation, they are the must calculation in the for your given system. Now, after you estimate the value of the cutoff for kinetic energy, wave function, and the charge density, you have to also find out the cutoff value of the K points. How? Progressively increase the values like this. I'll show you. So we had done the first calculation using a combination of Kx as 2 to 2. Next, I'll take a combination of 333. So which means we are allowing more number of K points in a given Brillouin zone. Run. Okay. So taking more number of K point in a given Brillouin zone further decreases the energy of the system. So in summary, the SCF convergence calculation, you need to find out the values of the cutoff of kinetic energy, wave function, charge density, and the K point. And accordingly, you will get the value of the energy. I hope it must be done by now. It's done. So you got the energy as minus 91.3375 and something. Achha, one more thing. We got a very frequent question from our participant that, sir, you are keeping a note of these energy in up to 6-7 decimal digits. Why is it so? Note down. You will also have to do it because these energy are being in the Rydberg unit. In your manuscript, you are going to put up the value in the kilocalorie per mole. So converting the Rydberg to kilocalorie per mole, the energy becomes substantial. So therefore, please do not round it off to up to 1 or 2 decimal digits. Next, the first calculation estimation of the cutoff. For the silicon cubical lattice, we have got these cutoff value as 35, 140, and 666. Participant, one more message that these cutoff values, it depend on the type of the element and the type of lattice you take. As in, if you are taking the silicon in 10 different crystallographic form, starting from the cubical one, the hexagonal one, in the different arrangements, the different Bravas lattices, the cutoff values of kinetic energy, wave function, and the charge density will remain same because these two remain dependent on the type of element. What will change? The moment you change the lattice, the K point cutoff value will change. So note down whenever you are taking the same lattice, whenever you are taking the same element in different lattice form, you don't have to do these calculation up to over here. You just have to use the value of 35, 140 for the silicon. However, if you are going to modify the lattice, you need to definitely do the K point calculation. I hope this part is clear. Now we will be switching on to the band gap calculation, the most fundamental calculation which majority of the researchers are interested in. So participant, there is a one. Okay, so these energies which we are seeing over here, they are the absolute energies. And till date, there is no experimental approach, experimental methodology, or any kind of an instrument which will predict the absolute energy of the system. So therefore, how to validate our result? Validation of the result means that these cutoff values they are the correct one. So what we basically do, we compute the band gap at all these combination. Why is it so? Because band gap we can easily compute experimentally using CV measurements. You have the UV measurements, CD measurement. There are a couple of measurements which provide you the band gap. So if your estimated cutoff values they are the correct one, as in this function, if these values are the correct one, the band gap obtained at this particular combination, as in 0.6115, it should perfectly match with the experimental value. So how to find out the band gap? Now we are moving on to that part. Pretty easy part. In the same SCF calculation itself, you can define the cutoff values. Like for the silicon cubical lattice, it is 35, 140, and the converged values over here are 666. How to reach the converged value? I am again iterating. Reaching to the converged value, just take the combinations, obtain the energy, plot a graph, see at what stage you reach the saturation. That is going to be the cutoff value. At those cutoff values, you need to do the band gap calculation. How is it so? Change the occupation to the fixed, and define one external command in the input file by yourself. That is NBND equal to 32. Now, why is it equal to 32? We need to have a detailed discussion onto that, but right now the time will not permit me. So NBND equal to 32. It defines that how many valence band and how many conduction band we need to analyze so that we will get the value of the band gap. So defining this command over here, clicking onto the upward arrow, take the NBND command to its position, cross it, and then 3 lines, and then run it. So it will not take much time. So band gap calculation using the SCF, simple one. Go to the input file, manually add the command NBND is equal to some mathematical value. Wait for a minute. It's taking a lot of time. SCF NBND 32. It's over. So like that, you can see initially red color flag was there. That means the calculation was running. It eventually turns to green. That means the calculation is over. And now the file disappeared. To analyze the value of the band gap, you need to open the log file and look for the keywords as in highest occupied and lowest unoccupied band. So these values are written over here. The highest occupied energy level and the lowest unoccupied energy level. Is it visible to all of you? I know this is pretty small. Is it visible to all the participants? Is there any way to maximize?
Yes, sir, it is visible, but you can
Great.
zoom if it is possible.
Zooming option in the Burai, I don't think so it is possible. Uh, so coming to this part, you get the value of the highest occupied energy level, which
Sir,
is basic.
So please hide that option, Google Meet sharing option. Hide.
In Google Meet sharing, is it
Hide. Click on hide.
click on hide?
Ah, okay. Thank you.
So now coming back to this part, the highest occupied energy level, which is basically the valence band, the lowest unoccupied energy level, which is basically the conduction band. Now, what we need to do it, we need to take these values 5.9849. We estimated this part for which combination? This is we estimated for this one. The values are already over here. The energy of lowest unoccupied conduction band, they are written in an incorrect way. They should be rather reversed. 5.9. The energy of highest occupied valence band, it should be 5.9849. And the value corresponding to energy lowest unoccupied conduction band, 6.5963. This I can show. So this is the value of the highest occupied valence band, lowest unoccupied conduction band we had obtained. Now to obtain the band gap, nothing much is there. You just have to subtract down these values. And subtracting these values, we get a band gap value of a 0.6115. But whether this is the correct one or not, that's what also we need to validate. At this stage, some of you may have a question that, sir, silicon cubical lattice, it is widely known to be a semiconductor material with a band gap value of a 1.12 electron volt. Note down the energy unit over here, it has changed to electron volt. It is no longer the Rydberg now. So some of you may have a question that, sir, electron volt 0.6115 silicon material, how it could be possible? So what you can do it, I'll show you one online database, the very robust database for the electronic structure based calculation result and some crystallographic results also. The materials project. It's again an open access one, all of you can use it for the free. So when you will come to this website for the first time, here in the option of login register will be there. Click onto that. You can use your Gmail ID to log in, then start exploring material. So now to find out the silicon property, click onto the silicon, click onto the search panel, and the database in this that you have got 43 different type of materials already enlisted in the database. All the way you can see silicon can crystallize in the cubical lattice, monoclinic lattice, hexagonal one, orthorhombic tetragonal one. I can see that 6 type of crystal system I can definitely see. Triclinic, I don't know whether it is reported or not. Even with the same type of a crystal system as in cubic, different atomic arrangement, different type of space group is also reported. Now, please have a look at the value of the band gap enlisted over here. So you can definitely see that the band gap is a function of not only the type of element you take, it is also dependent on the type of crystal system you take and also the atomic arrangement as in their corresponding space group. So the conventionally known silicon semiconductor material for which the band gap is widely known to be 1.12 electron volt, it crystallizes in the hexagonal lattice with a space group of P6 triple M. On the other hand, what we have taken a cubical lattice with, when you click onto the ID, you will be able to see the structure. So we are basically working on this structure, silicon atom at the corners, silicon atom at the face center position, and silicon atom at the tetrahedral void. And that is why their band gap value of 0.61, rather our band gap value of 0.61, it perfectly corroborates with the experimental reported value. So therefore, using the value of the band gap, you can always validate whether your computed values of kinetic energy wave function, charge density, and the K point are they correct or not, because you have to use these values for all successive calculation. So that's how you can easily estimate the band gap. Now, how to take these materials structures to the Burai interface? I'll just quickly show you, and then I'll take all of you toward the next type of calculations. So let us say if you want to work on this silicon hexagonal P6 triple M lattice, you just have to click onto this ID. Here in the option of export as is also available. Click on it and then click onto the SIF. And when you click onto the SIF, its unit cell structure will be downloaded. How to take this structure to the Burai interface? So just cut it this SIF file. In the C drive itself, you create a new folder with the name SIF, or otherwise you can give any other name of your choice, that is up to you. In that SIF folder, drop the downloaded file. So that's how you can take n number of files to be investigated in the Burai interface. So how to open this file in the Burai now? You have the option of My Computer. Under My Computer, you now see the folder which you have created. And here in the option of the file which you have downloaded, you can see that that was silicon SIF. This is the one. So that's how the structure of silicon as in the hexagonal form with a space group of P6 triple M look like. On this structure, if you are going to do the band gap analysis, that will perfectly match with the 1.12 electron volt. I think we have done those calculation and results. If I show. So that will take a time. Rather, I'll share these folders with all of you if you need it. Achha, one more thing that participant, there is a precaution. The precaution is the pseudo potential files which we have defined over here. They are defined for the neutral or in the neutral form of the element, not for the cationic or not for the anionic form. What does it mean? If you look at the example library of the Burai, this is a precaution you have to take whenever you are going to deal with the inorganic substances, as in this calcium sulfate. Calcium sulfate, it is a neutral substance overall, but calcium plus 2, sulfate minus 2, sulfur plus 6, oxygen minus 2, it should be there. But note down, under the atom column, you will not see the charges. You will see all of them in the neutral position. So therefore, what do you have to do it whenever you download any SIF from the databases? Like this is the one file we have downloaded. So this is the structure of the MGAL204. So whenever you download any structure from any database, please remove all the charges and then only you execute the calculation. Otherwise, you will observe spin multiplicity error. So if in case of spin multiplicity error you are observing, please remove charges from all of them. And how to remove them? Pretty simple. Double click and backspace and erase it. You can also do it in the notepad also. MGAL204 in the notepad also. Simply drag this MGAL204, the zip file, and now you can remove all these plus charges. We'll see there is an option of edit. Go to the replace, write down the charge, and under this replace, leave it blank. That remove the charges from all the magnesium plus 2. Similarly, sulfur plus 6, oxygen minus 2, and then you reopen the file in the Burai. That will do the part in an easier way. Otherwise, there are 56 number of atoms. It will take a lot of time. So that is the only precaution you have to take with the inorganic charged substances. One more thing, which our previous participant they had a doubt with the organic systems. With the organic system, the typical question which were asked by some of the participants were C67. C67. So participant, this is a unit cell structure of a C60 as in the following. Our previous participant before they were doing the band gap analysis, band gap computation, they had a doubt that sir, in this unit cell structure, we are not able to see a discrete complete fullerene unit. So if using this structure, we are going to estimate the band gap. Will that band gap corresponds to the fullerene unit, or we need to double the computed band gap? Nothing like that. You can do one thing. You can go to the modeler option. We are going to detail this modeler option after a couple of minutes. Right now, I'm just showing something so that we can complete the band gap part. So what you can do, you can always do the translation over here. Now, I am sure that you must be able to see a complete fullerene ring within this lattice, the middle one. So therefore, please don't get confused that if a given cell structure does not consist of the entire molecular unit, it is not there. It has to do with the definition of the unit cell. A unit cell may consist of entire molecular unit. It may not consist of entire molecular unit. So you just have to use the structure to do the proper calculation. So that's how you can estimate the band gap. I just summarize. Till now, what we have done, we have started with SCF convergence calculation. SCF convergence calculation bring down the energy of the system by tuning the three variables: the kinetic energy, wave function, charge density, and the K point. We are minimizing the energy so as to maximize the stability. How to maximize stability and minimize energy? Tune the variables in a specific ratio starting from 1 to 4 to 8, 1 to 12. That is a pure, the final result will remain same. Increase the value so that the energy saturates a certain change. Similarly, for the K point also, you need to increase the value constantly and better the energy. Once you get the cutoff value, please do the band gap calculation at the cutoff value and see with your experimental results or with the theoretical results which are already available on the literature. So band gap calculation now we are, and now I'll move on to magnetic property calculation. So let's see if I'll close these graphene. All we are going to see in the second half of the session, that is showed at 3 p.m. Now for the magnetic property calculation, I'll take an example of the iron lattice. So iron unit cell structure cubical form. This is the PCB arrangement. You can download some another form of iron unit cell from the database. I'm taking the one which is already available in the Burai interface. So to compute the magnetic moment of this lattice, how the calculation proceeds under element. Again, same thing, taking the solar potential to the ultra soft one, because ultra soft. One more thing, we had the discussion about ultra soft solar potential and the PW solar potential. At the beginning of the session, I said we first take the ultra soft solar potential. If the result accuracy is not enough, sufficient enough, then only we take the more time consuming PW based solar potential. So we have done one such calculation of the band gap. Our computed value of the band gap came around 0.61, which almost perfectly matched the literature report was 0.610. So therefore, I don't think so. We need to on the PW based solar potential. So please note down ultra soft first choice. If not appropriate, then only PW, because switching from ultra soft to PW, the calculation time will exponentially increase. Great. One more thing, researchers call The band gap we are getting within a couple of seconds. The band gap calculation can take around half an hour also, depending on the complexity of the system. As the silicon physics triple M lattice I showed you that have almost like 20 number of atoms. If you do the calculation of that lattice, it can take around 30 minutes on your normal laptop itself. One more thing, if you would like to do this quantum espresso based calculation on a very big system on online servers, there are some online servers also. So that I'll discuss in the second half of my training session. So moving back to the iron lattice, how to set the calculation for magnetic property estimation. Go to the pseudo potential in the pseudo potential file. Atoms at this stage, I would like to do one thing because only iron will not be able to see much part. I'm changing the second type of iron atom which was present at the body centered position with cobalt because cobalt is also magnetically active, iron is also magnetically active. So let's see some results and then I'll discuss why we had changed it. So next, move on to SCF and note down over here to do the magnetic property calculation, you need to keep the cutoff values. I repeat, if you want to do the magnetic property calculation, you need to keep the cutoff values. And to get the cutoff values, you need to do the SCF convergence calculation. So what is the chronology? The chronology is first SCF convergence calculation to obtain cutoff values, second magnetic moment. For this lattice, we have already done the calculation and I'll show you the result for that. But before the how to set up the calculation, so we are keeping a value of 46 over here. 46, right? Yes, 46 to 37. And how we reach to 46 to 37? We had priorly done the SCF conversion calculation to obtain these values. K points I'm keeping 444, steering and changing to the Fermi dark model. And now we need to move on to the magnetization. Now, under the magnetization, you are seeing polarization as a collinear model. There are three options available over here: the non-polarized, the collinear, and non-collinear. If you look at the lattice corresponding to silicon, widely known to be magnetically inactive. So by default, the Burai will show you it is non-polarized. You don't have to do any over here. However, whenever you are going to deal with the magnetic samples, magnetic atom, the software will show you polarization as a collinear. Now, why it is showing the collinear model over here? Because magnetic moments associated with each and every electron in the given lattice, it is vector quantity. So on the application of the external magnetic field, the individual magnetic moments they will uniformly align as per the direction of the applied magnetic field. And that's why the model by default going to the collinear model. You can always change the collinear model to the non-collinear one, but majority of the materials which you are going to estimate, you are going to study follow follow collinear statistics. So therefore, better leave collinear only. Check the accuracy of result. If not accurate, only then switch on to the non-collinear model. Now, I'll come to this part. Similar to the cutoff estimation for the kinetic energy wave function charge density and the K point. Now you need to find out the cutoff value of some parameter over here. What is parameter? This parameter corresponds to the starting magnetization. What is the meaning of this starting magnetization? What are the ranges of it? The starting magnetization defines that on the application of external magnetic field, how individual magnetic moments they align with respect to each other. As in, it has got a range of 0 to 1. 0 defines that when you apply external magnetic field, all the magnetic moments they cancel out with each other. How come? 50% of the individual magnetic moments they must have aligned parallelly to the direction of the applied magnetic field. 50 will be going opposite. And in total, all the magnetic moments cancel out. The value will be equal to 0. Similarly, a one value depend indicate that all the individual magnetic moments they are aligned as per the direction of the applied magnetic field. And that's why 100% contribution to the magnetic moment, the value 1. Now, under the practical situation, I don't know what is going to happen. How many individual magnetic moments will align parallel to the direction of the applied magnetic field? How many will go opposite to it? So therefore, what do you have to do? Practically, you need to tune the value starting from 0 up to 1 with a step size of 0.1. Do not take less than that because the graph already will be getting the continuous within the step size. So, conclusion, what do you have to do? You need to change the value of the starting magnetization from 0 and reach up to the value of a 1 and obtain the energy of the system. Similarly, for the volt also, you need to change the value of the starting magnetization all the way from 0 to 1, obtain the energy of the atoms. And what kind of results you are going to get, I'll discuss that part. But same you will have to do on the SF converse calculation. Now let's see the result part. So this is the result we have obtained for iron unit structure. So what this calculation, this table will go to menu script. What this calculation indicates that we have taken the cutoff value of the kinetic energy wave function, charge density and the K point. So there is no change over here. what we had done, we had changed the value of starting migration. This was the only iron lattice. Next, I'll do it for iron gold lattice. We had changed the value of starting migration all the way from 0 to up to 1.0. And these are the corresponding energy of the system. Energy we have seen in that graphical form. Now, next, what do you have to do? You can take this data to a new workbook, or then you can plot a graph. Otherwise, say what you can do, you can click on the BIN, click on smallest charges. Why is it? So because we need to estimate the value of the starting migration at which energy is least. That means the system is most stable. So this is the value of the starting migration for the iron atom in the cubical lattice BC form 0.5. So all successive calculation whatsoever I am going to do it, I will keep the cutoff value of starting migration for the iron cubical lattice as 0.5. So that's why you can easily obtain the cutoff value for the starting migration as well. Now participant, here say how we have estimated the value of cutoff kinetic energy wave function chart and key point. We systematically tune the value till the energy difference or till the energy change become very near. This is not the case for the starting ionization. You are bound to scan the sample all the way from 0 to 1. You cannot stop at any intermediate stage. You have to scan. See, energy may increase, energy may decrease. You have to scan the sample all the way from 0 to 1, and then you need to find out at what particular starting ionization energy is least. So that's how you have to approach. You can do one more thing. You can always plot a graph to see the lowest minimum. So that's what it looks like. Energy change very near over here, and at suddenly 0.5 energy decrease substantially. So this is going to be the value of the starting ionization. I'll jump on this iron cobalt lattice because there is something over here. So iron cobalt lattice, what do you have to do it? See, this is the starting ionization for the iron. We are keeping over here because I had not changed the lattice, it's still chemical form. I had not changed the element, it is still iron. So we kept the value of starting ionization constant 0.5. We changed the value of starting ionization for the gold all the way from 0.0 to we need to go up to 1.0, but I stopped at the stage of 0.7 only, 0.6 only. Otherwise, you have to go up to 1.0. Now, what is the nature? The nature of the graph is like this one. Initially, energy decreases. It reaches the energy minima at 0.3. It again increases and then it again decreases. So there are two local minimas, but we have to find out global minima over here. See, if you are going to extend the study up to 1.0, because we have that this is what the updated result. If you are going to extend the calculation up to 1.0, you will see other minimum at 0.8. Some of our participants they had said that. So in that particular case, the starting ionization cutoff value will be 0.8 for the volt. So that's why you can easily obtain the cutoff value for the starting ionization of bimetallic system as well. And now I'll come back to these values. So in this table, there are a few more things we have listed. These are the value of the total ionization in the unit of Bohr marathon. So how to read these values? Let me do one calculation so that we can have the result. So let me keep the cutoff values here 0.5. Participant, there is one precaution because this is what we are observing with our participants. They usually change the value over here but don't press the enter key. They are in somewhat little bit hurry, so immediately go to the icon. Please don't do that. The moment you type any value, please press the enter key. Because unless and until you press the enter key, the Burai will not take the updated value. Similarly, over here, I'll keep the cutoff value which we estimate using the SCF convergence, and now we will do the calculation. I'll just show you one calculation so that you will know how to do the manual calculation. Name and all, you can keep any name of your choice. There's no rigid condition that the folder name is like this or that. So it will hardly take a minute. So one more note to all of you that definitely you will be attempting these calculation after session from the recording part. I know this is a little fast, but recordings will help you out over there. The quantum espresso based calculation, since it defaults to the DFT model, the plain wave DFT model, it can take a lot of time. It can take a lot of time. Sometimes it can go up to 4 days, 5 days, 6 days also. A single calculation. So please don't do those kind of calculations which take around 3, 4, 5, 6 days in a stretch. Rather, there are ways to minimize the calculation time by changing so many variables over here. Like you have got one variable under the electronic optimization, then you got the something like the F maximum step. So I cannot discuss these things right now because of the limited time. The message is, if in case any of your calculation is taking a more than day, please don't do it. Rather, immediately stop it. Now, coming back to the result of this calculation. See, the log file always consists initially the results of the iterations, the calculation. We are never interested to see those parts. I am interested to see the final result. And to see the final result, you have to always scroll down to the last and then gradually come up. Whether you want to study the band gap or whatsoever. So I can see the value of the magnetization as in the Bohr magneton, it comes out to be 4.8 Bohr magneton per cent. This is for the iron cobalt lattice we have done and we did it at 0.8. The value came out to 4.8 Bohr magneton. Now, there are additional informations which are lying over here. What exactly is that? I am sure all of you must be aware of out of iron and cobalt, which is more magnetically active. So out of iron and the cobalt, iron it has got more number of atomic electrons as compared to cobalt. So therefore, iron is more magnetically active compared to the cobalt. But what exactly is going to be the magnetic moment in a given crystallographic form, in the metallic bonding form? You can also investigate that. The information corresponding to magnetic moment per site, it is there. So value will be written over here, magnetic moment per site. This is over here. Atom number one, atom number two. Atom number one, in our case, it was the iron at the corner position. The software says it has got magnetic moment of 2.9, and the atom number two got a magnetic moment of 1.9. So that's how, as type of different type of atoms you have in the unit cell, in the lattice, you can study their individual magnetic moment also. And the total value you have already seen at the last, the 4.98 something. So I am sure that how to put the magnetic moment calculation must be clear all of you. I'll just quickly summarize. Under the magnetization, before that, under standard setting, you have to keep the cutoff values. So SC convergence calculation to obtain the cutoff value is must for the magnetization. Then go to the magnetization. And under the magnetization, keep the polarization as polar by default. Obtain the cutoff value for each one of them. Keep those values and then obtain the magnetic moment total one and individual magnetic moment. I'm sure this must be clear. Although there are a few more things we need to discuss, but we'll move to the next part. In the next part, I will be discussing about the structural optimization. But before that, may I know how much time I am left with?
Almost done, Dr. Nikhil.
I can see that. So structural optimization, the molecular design, the nanoparticle design, band structure and DOS, MD studies. I'll take the second half of my part, which is scheduled at 3 p.m. Okay. Now, please, if you have any question, we are over here. You can definitely raise. Other than second half, we can take that time is not.
Okay, sir, thank you for my session, in which you have shown how we can minimize the SES value and how we can calculate band. Thank you very much, sir. See you at 3 p.m.